Hello everyone, my name is Shashidharan Rao. Welcome to our presentation. We are Group 4 and today we will be presenting our artificial intelligence final project titled Posture Assistant AI Power Ergonomic Monitoring System. This project uses artificial intelligence to monitor a user's sitting posture through a webcam and provide real-time feedback. The goal is to help users maintain good posture, reduce the risk of back pain, and promote healthier sitting habits. Our project also supports Sustainable Development Goal 3, which focuses on good health and well-being. Let's begin by looking at the problem our project aims to solve. Today, many people spend long hours sitting in front of computers for work, studying, or entertainment. One major problem is that people spend most of their day looking at screen, often without taking regular breaks. Another issue is that many people do not notice when they are sitting with poor posture. By the time they feel pain, the damage may have already started. According to the World Health Organization, back pain is one of the most leading causes of disability worldwide. Although ergonomic chairs and posture support devices are available, they are often expensive and may not be comfortable for long-term use. Because of these challenges, we developed an AI-powered posture monitoring system that only requires a webcam, making it simple and affordable solution. The first objective is to build an image classification model using Google Teachable Machine that can accurately distinguish between correct posture and slouched posture. The second objective is to design a real-time monitoring system that provides immediate visual feedback to the user. The third objective, the third objective is to evaluate the model's performance under different lighting conditions, camera angles, and distance. Finally, the project aims to contribute to Sustainable Development Goal 3 by providing an accessible and low-cost solution that encourages healthier posture habits. Next, we will continue with project scope.
Thank you and hello everyone. My name is Muhammad Irfan bin Abu Bakar and I will be guiding you through our project scope and the design of our solution. Looking at this slide, we have outlined the specific boundaries for our current prototype. First, we simplified the problem into two classes, distinguishing between a straight upright posture and a hunched over slouched posture. The platform we choose for this is Google Teachable Machine, specifically using their standard image model. For data collection, we get the image via webcam, deliberately varying the angles and distance to give the model better context. It is important to note that this is a software-only prototype. Physical hardware like vibration motors are outside our current scope. The system is designed for indoor and best environments, optimized for typical home or office lighting conditions. Finally, at this stage, it operates as a single user prototype, meaning it has been trained and tested primarily on one individual. Alright, moving on next slide. Let's look at how this actually work in practice. This flowchart illustrates our system journey from webcam input to real-time feedback. It operates in a continuous loop. It begins with the webcam input, which captures the user as they sit at their desk. This feed goes through image capture and pre-processing before being fed into our core engine, the teachable machine model. Under the hood, this uses a mobile net convolutional neural network, a lightweight AI structure perfect for running smoothly in the web browsers. The model then performs posture qualification. It detects a slot, the loop close by intensely, providing the user with real-time feedback on their screen. prompting them with please sit up straight because all of these runs client will cite via TensorFlow.js. It is incredibly fast and completely private. I will now pass the presentation over next person to discuss our test preparation in more details. Just that from me. Thank you.
Assalamualaikum. My name is Muhammad Irizan Irfan bin Hisham. My metric number is B0325101132. Today I will explain how we prepare the dataset for our posture detection model. To collect the training data, we use the webcam provided in Google Teachable Machine and capture image ourselves. As shown on the slide, these are actual image from our dataset rather than sample image from the internet. We divided the dataset into two classes. The first class is upright, which represent the correct standing posture, and the second class is slouch, which represent the incorrect posture with a bent back. We collect 12 images for the upright posture and 17 images for the slouch posture, giving us a total of 29 training images. During data collection, we ensure that the image clearly represented each posture so that the model could learn the visual difference between the two classes. Although the dataset is relatively small, it was sufficient to train a working prototype and demonstrate the concept of real-time posture classification. However, as mentioned in our proposal, our target was between 15 and 100 images for each class. But due to the limited project duration, we were unable to reach that target. Therefore, expanding the dataset with more images, more people, and different environments will be one of the main improvements for future development. After that, we move to next slide. After preparing the dataset, the next step was training our artificial intelligence model. We use Google Teachable Machine, which applies transfer learning using MobileNet as the best architecture. Instead of building a neural network completely from scratch, transfer learning reuse the knowledge from a MobileNet model that has already been trained on millions of images. We only train the final classifications layer so that it could distinguish between upright and slouch posture. This approach is especially suitable for our project because it requires fewer training image, less computational power, and much less training time while still achieving good performance. For the training configuration, we use 50 training epoch, a batch size of 16, and a learning rate of 0.001. Once the training was completed, the model was exported to TensorFlow.js. This allows the model to run directly inside a web browser, which means all posture detection is performed on the user's own device without sending webcam image to an external server. This helps improve both speed and user privacy. Overall, using MobileNet together with transfer learning enable us to build a lightweight and efficient posture detection model that is suitable for real-time monitoring. Now uh, I will pass to my teammate. Thank you.
Assalamualaikum and hi, my name is Muhammad Zuhilmi bin Saril. My matrix number is B0325101106. Now let's move on to the slide 8. Moving on to slide 8, let's look at how we tested and evaluated our prototype. We set up our testing phase to stimulate a standard test setup evaluating the model exclusively under bright indoor lighting. Our goal was to assess how well the system performs at varying distance and angles from a standard laptop webcam under consistent, well-lit condition. Now let's see the video. Now, if you look closely at the live confidence readings in the recording, you'll notice an interesting technical detail. When I am sitting upright, the prediction reading fluctuates slightly and is not always at a perfect stable 100%. This is because small shift in head tail, shoulder placement or micro adjustment in distance can cause slight variations that make the upright posture a bit harder for a basic image model to generalize, even in bright light. However, look at what happens at the moment I slouch. The slop posture reading is incredibly accurate and stays locked in with solid confidence, because slouching creates a very distinct, curved silhouette of the neck and spine. The mobile net can easily isolate and classify this state without confusion. This is actually a highly positive result, as our primary goal is to ensure that unhealthy slouching is detected reliably. As we just saw in the demonstration, we successfully achieved our main objective, which is we built a function end-to-end real-time posture monitor that successfully alerts the user. However, analyzing the fluctuations we observe in our testing video helps us pinpoint our current limitation. First, our training dataset is small, consisting of only 29 images from a single user. Because of this, the model is slightly sensitive to background environment and camera angles. These fluctuations can prove that an image-based model can easily get distracted by subtle changes in the frame. This is why our future work, we plan to transition from simple image classification to coordinate-based pose models, which will look at skeletal landmark rather than raw pixel. This will eliminate the reading fluctuation we saw today and make the system generalized to anyone. So that's all from me. Let's move on to the next speaker.
Assalamualaikum and hello everyone. My name is Muhammad Shazwi Azim Bahar and I'm going to explain about our conclusion and future work of our project. To conclude, Posture Assistant proves that we can build a functional, low-cost ergonomic tool using an accessible platform like Google Teachable Machine. By helping users fix their sitting posture in real time, this project directly supports SDG 3 for good health and well-being. Looking ahead, we have 4 next steps to improve this prototype. First, we will expand our dataset to 50 to 100 images per class across different people. Second, we will test the system against different users, clothing, and backgrounds to ensure it generalizes well. Third, we plan to explore teachable machines post-model for better person-independent detection. Finally, we want to add lightweight screen or audio alerts and explore optional hardware feedback. That's all from us. Thank you for your time.